Okay, so you guys read about mixtures and you answered some questions. I just want to formally go over it to kind of break down a couple things that I think are important. It's actually a relatively important section with a lot of good information. So you learned that a mixture is a combination of two or more substances, but remember they're not chemically combined. So right away we're starting to see the difference between a compound and a mixture. Remember we talked about compounds, they are not chemically combined. Or excuse me, compounds are chemically combined in set ratios. Where a mixture, think about a pizza, great example. You know, you can throw as much pepperoni on there as you want, or cheese or sauce, and it's not in a set ratio and it's not chemically combined. We can take all those parts to the pizza and take them apart, and they are not something different when we put them together and take them apart. So this is a really good chart that I hope you guys looked at on your pages. So this distinguishes between mixtures and compounds. So we have elements and compounds, or both with mixtures, but we really only have elements with compounds. And in mixtures, we don't have a change in the original properties or of the components. So think about that pizza example. Whereas in compounds, we talked about the physical properties change from the original substance, or excuse me, the original elements by themselves. After they're chemically combined, now they might look completely different. We can separate mixtures by physical means. We have to separate compounds by chemical means. And remember that ratio can be any ratio with mixtures, but it's set with compounds. So this is a great chart to take a look at. So we also have what are called solutions. So these are homogeneous mixtures of two or more substances that are uniformly dispersed throughout a single phase. So when we use that term homogeneous, think of homo as the same. So the mixture is very uniformly dispersed. So when something dissolves, we use that term all the time, right? The particles of a substance separate and spread evenly throughout a mixture. So when we're talking about dissolving, we have what's called the solute in a solution. This is the substance that dissolves in the solution. So it's whatever we want to sort of, like, we use that term melt a lot or dissolve. And the solvent is the substance that we put that solute in to dissolve it. So a real example of that, which we would be doing if we were in the Queen of Peace building, would be a simple experiment with milk and chocolate bars. So my grandma used to make homemade chocolate milk without like Hershey syrup or like Nestle Quick. So she would take really nice candy bars, like good chocolate candy bars, and we'd put milk on the stove and we'd melt the chocolate bar, right? So the solute is what we want to dissolve, right? So the solute would be the chocolate bar. The solvent is the milk, right? So that's what we're going to put that chocolate bar in to dissolve it, okay? So that's important to note. We have the solute and solvent. There's lots of different examples of this that you can probably think of. For example, if you've ever had Kool-Aid, that's another example of a solute and a solvent. So the solute would be the actual powder, sugar powder Kool-Aid, and the solvent would be the water. So if we were in class right now, I would say, give me two examples. I just gave you two examples, so I bet you can think of more, as I said. So some examples of solutions. These are kind of complex solutions, but there's pretty simple ones that we could talk about, right? So a gas in a gas would be dry air, which has oxygen and nitrogen in it. Gas in a liquid would be soft drinks where we have carbon dioxide. In a liquid, water, for example. I showed you my bubbly drink the other day. That's a great example. Liquid in liquid, antifreeze, which we put in our cars so that things don't freeze up, is alcohol and water. Solid and liquid, salt water, right? We put the salt, which is a solid, in the water. That's a mixture. It's not chemically combined. It's a solution. And a solid and solid. So brass, which is an alloy of zinc and copper. Sometimes we have furniture or different things made of brass. So these are kind of scientific examples. I bet you can think of some that are not. So we talk about concentrations, and that is a term that we're going to be really familiar with because we're going to be doing a lab. So it's the amount of a particular substance in a given quantity of a mixture or a solution. So we concentrate things. So if something is soluble, it can be dissolved in something else. So we talk about things that are water soluble, right? So if something is really concentrated, go back to thinking about the solute and the solvent. It has a lot of solute in it. So it has a lot of Kool-Aid in it. It's going to taste really strong on the Kool-Aid side if it's really concentrated. Some of your guys' parents might get orange juice that's frozen, You probably, if you don't do this, are like, what are you talking about? But you can go to the grocery store and you can get a can of orange juice where you add 1 can, the concentrate. It's called orange juice concentrate. So it's really, really strong, frozen. And then you add 3 cans of water to it. So you're adding to the solute, the solid orange juice that's very, very strong. You're adding water, you mix it up, and you've got orange juice. It's a little more reasonably priced than buying a pitcher of orange juice, so a lot of people do it that way. But the point is that you have a solvent, the water that you're adding to the solute, the orange juice. And so if it was really, really sweet tasting, you would have not enough of the solvent in it, not enough water in it. So it would be what we call very concentrated. It has a lot of the solute. If it's diluted, we use this term diluted, right? It tastes kind of watery. Like, for example, if you've ever had like Crystal Light or Kool-Aid or even that orange juice I was just talking about, sometimes you can add too much water to it, too much solvent, and it's like super watered down. So we say it's diluted. So your book gave this example of, this is actually what we call copper sulfate. And we could done a lab with this at QP before where we look at it and can see. Obviously you can see this one on the left is more diluted. So it has more of the solvent in it. And so it's lighter colored and there's a lot less of that copper sulfate in there. So there's a lot less of the solute. Here, wow, look at all this. You have a ton of the solute, the copper sulfate. So this is going to be really strong, right? This is going to have a very concentrated taste, right? So we use these terms, and it's very important to note that if something is more concentrated, it has more of the solute and less of the solvent. If it's dilute, it's less solute, so it's kind of watered down with more solvent. So very, very important to think about as we move into doing some other stuff. So we would be able to do this lab with copper sulfate. If we were in the science lab, we would use the Bunsen burner. If we stir something, and that's why you stir things on your stove, right? You can get those particles to separate from one another. The heat gets them to them, and it kind of moves the heat around. So that's important. That's in the middle. Mixing, stirring, right? Same thing. You're kind of moving the particles around. Heating is even better. Crushing, right? Think about my giant chocolate bar. It's going to take a lot longer to melt if it's a giant chocolate bar versus if I break it into a bunch of pieces. The heat can get to all those little pieces, and more of the surface of the chocolate bar around the outsides. If we break it into a bunch of pieces, it is more surface area exposed to the heat, right? So we to get things to dissolve more quickly, and we would be doing this in school if we could. We mix, we heat, and we crush, or what we call pulverize it. So a lot of us do this in our everyday lives when we're cooking food and we don't even know it. So a couple more things here. We have what are called suspensions. So these are mixtures where those particles of a material are very evenly dispersed. You don't even notice it, and they don't settle. Like, for example, they actually do settle, sorry. So for example, if you've ever shaken up a snow globe, those particles rest at the bottom and you got to shake it up again. If you've ever painted, right, oil-based or water-based paints, the water and the oil settles at the top, and you definitely want to stir them up because that mixture settles out. So it's important to do that. Medicine. How many times have we taken medicine that we have to shake up, right? Because the medicine particles end up being concentrated at the bottom, so we want to mix them up. That's another great example of a suspension. Simple ones in your refrigerator, salad dressing and ketchup. You have to shake them to be able to mix them up so that you don't get too much or too little of the watery part or the, spices in the salad dressing. So these are all suspensions, right? They have to be shaken and the particles are heavy enough to settle. Others that we don't think about that are mixtures because the particles aren't big enough to settle out: milk, mayonnaise, Jell-O, deodorant. These are all things that are mentioned. They don't settle out because the particles are mixed together and they're not big enough to settle out like they would be in the suspensions like we just talked about. Okay, we've gone through these notes. Hopefully you understand this because we're going to be doing a little bit of work with this very, very soon.